Yeah. No, before. I think, well, if the spirit code is, let's see. What very and the result. All right, well, it is 5:30, so I'm going to get started. I'm just checking to make sure the mic is working. If you are attending this class remotely, please use your voice to ask questions because I'm not going to read the chat on Zoom. And the one thing Zoom does not do is it doesn't even alert you with a notification when there's a new text appearing. So that makes it kind of difficult to use the text chat for communication in the class. So if you're online, please use your voice to ask questions. This is kind of the outline of what we're going to do today. Forget about the critical thinking part. Not that it is not important, but it is not related to this class. I was taking notes for one of the meetings that I was in, and one thing that I wanted to ask the one of the presenters was, how the presenter introduced and taught critical thinking in his classes, and that was a chemistry class. You might even know that professor. I think his name is Mike Hain. In the chemistry department. Some of you may know him, and most of you do not need to take chemistry classes. Anyway, the exam 2 score is out, so you can check your grades. It is after adjustment already. The adjustment is multiplying your original score by 4 and then divided by 3.35, because the 5th highest score in the class unadjusted was a 3.35. So that's exactly what I promised that I would do, and that's exactly what the score you'll be looking at. If you do have any questions about the score, because I have not found a way to easily incorporate my feedback directly into Canvas. The score was easy, okay? It was just a spreadsheet thing, it was easily imported. But the comment that I have made for each one of you, for each exam, there was no easy way to import that into Canvas. So I can do that manually, which is going to be painful, but I can do that. It will just be a lot of copy and paste, looking up student ID and stuff like that. But if you do have any questions, just send me an email and I'll try to respond to those email messages as much as I can. All right, so that's about exam 2. And now that we have exam 2 out, you can kind of figure out your current status in the class. All the labs basically add up to 0.2 of your final score. Exam 1 is another 0.2, exam 2 is another 0.2. So what you do is you multiply your raw score in percentage by 0.2, for each one, and you add them up. And that would be the overall score that you're getting up to this point, not counting the assignment that was due today or the ones that I have not graded. But the homework assignments are not really taking up a lot of points, so it's not going to be significantly impacting your overall score, at least not nearly as much as the final exam, because the final exam is another 0.4 of your actual score. So if you add up these 3 items and it's already 30.7.5%, 37.5% or more, then you're already guaranteed a C out of this class. Okay, in other words, if you don't show up at all in the final exam, you can still probably manage to walk away with a C. Okay, which I'm not sure is a good thing or not, but I'm just telling you the fact. On the other hand, if you add up all these 3 and it's still not 37.5% yet, so that means you still need a few percent, depending on what your actual score is, from the final exam in order to pass this class with a letter grade of C or better. So is that okay? Is that understood? Yes.
Multiplying it by 0.2 or the actual score?
So each one is a percentage. So you take each percentage and you multiply that by 0.2 and then you add them up. That would be your weighted average, up to this point. So if that number is less than 37.5%, that means you have not passed this class yet. So the final exam may be important. The final exam is 0.4, which means, for every single person, it's at least 1 grade, difference. Okay, if you currently already have a C, if you do well in the final exam, you can end up with a B, possibly an A, depending on where you are, because 0.4 is a lot. 0.25 is the difference between the letter grades, right? So 0.4 is almost 2 grades. So that means doing well in the final exam can significantly change your grade. Even if you're passing right now with a C, getting the final exam done may bump it up to possibly a B, and depending on where in the C scale you are at. Because C spans all the way to 62.5%. So let's just say someone is right at 61%. Well, if the final exam, if that person aces the final exam, that will bump a C to an A. Yeah. So I think it is important to kind of look into the final exam. All right, so the third item here is I'm going to implement the Fibonacci program in class. So that's what I'm going to do next. So let's go ahead and do that. So what I'll do is go to the Fibonacci lab, because there's a little template of code in it, I think, or is it in the announcement? I cannot remember. It's probably in the announcement. So you take a look at the how to get started. Nope, not here. Sorry? Oh, how to get started. No, starter code, there we go. So I'm just going to use my own starter code here because most of you hopefully got this one. So we'll go ahead and get this one. And then you switch to a window like this. And we'll take a look at fib.-3.ptpasm. And the C code is not here anymore, but I can just write it on the side. All right, so I'm just going to write the Fibonacci code on the side here. It is unsigned or unsigned AB integer, but it's kind of the same thing here. So we'll just say unsigned N. Okay, so here is a choice. Do you want me to use the long version, the really verbose version, or do you want to use the original version, which consists only of one single return statement with a ternary expression in? Original? Well, the original is still step-by-step in the assembly implementation. It's just that in the C implementation, one gives you more chances of putting breakpoints and whatnot.
It goes like spelling error, sure.
Unsigned, yeah, because it's not in green. So I think I can do both. Okay, I can do both. We'll do the because I'm lazy, I'm going to do the easy one first, which is the short version, the terse version, and then we'll go back and do the longer version because that one really is a lot more code. Okay, so we'll do this one first. It's a single ternary expression which compares n. As long as n is less than 2, we return n itself. Otherwise, we return f of n minus 1 plus f of n minus 2. And that's the only statement. So that's what we're going to do. All right, so switching back to the assembly code side, this is f. So the idea of this code is to implement the structure as described by the C code. And the way we look at this is, okay, so there are a few things that I always do at first is I look at what is on the stack. The parameter n is on the stack, at a higher location, and then at a lower location, we have the return address, so that we can return back to the stack, back to the caller. This particular implementation does not have any local variable. which means at the entry point of F, the stack pointer is pointing directly to the return address. So just to make it easier to access N, I'm going to use a label Fn. It is basically just 1 because I have no local variables and the stack pointer is pointing to the return address. And the parameter N is 1 byte past the return address. So do we have any questions at this point about what the call frame looks like at the entry point of the subroutine? Yep.
So you're using the Fibonacci code to as a starting point for the recursive code.
Well, the name of the subroutine of the function is F. So in the assembly code, F colon is the entry point of the function. Is that okay? I'm not sure what the question is.
Are you solving the recursive code right now?
Yes. But I need to kind of get the entry point and the exit point and get all that stuff out of the way first. So this is just a label. I mean, the label is nothing more than defining an offset of where I can find the parameter N from where the stack pointer is pointing to at the entry point of the subroutine. So typically, I would also write the exit code right away, because if I don't do this, sometimes I forget. So I would do the exit code right here. The meaning of the exit code should be fairly clear by now, okay? Even though most people can look at this and just say, oh, it's just a pattern I have to follow. But there are other ways that I can accomplish this without using exactly the same 3 instructions in this particular order. So you will still have to be able to recognize that, oh, okay, so you are using what the stack pointer is pointing to as a place to return to. Okay, but this is the typical way that we return to a caller. So in between, now we can start to write the actual code. So when we look at the C code, the first thing we need to do is to determine whether N is really less than 2 or not. Is that right? Okay, so how do we do that? Well, this one, I think AND AA does not work as well. So it is actually better off for us to do a real comparison. So that means, I need one register to have the value of N and another register to have the value of 2, do a compare, and then do a conditional branch after that. All right, so we'll use register A as N, and then we'll use another register for 2. So the way to do it is, now this once again is going to look like a pattern, but you still need to remember what it means, why we are doing each one of these instructions, so that we get the value of parameter N into register A. So these 3 instructions will load the value of parameter N into register A. And then I use another one to load a constant of B, a constant of 2 into register B. Question?
So I understand the FNA LDI. So why are you adding the contents of D into A? Why are you adding the contents of D into A?
Because the label is defining how many bytes are between where the stack pointer points to and where I can find N. That is what the label is defining. It's just an offset. It's kind of like saying, you live like 2 houses down from where I live. So if somebody needs to find you, that person needs to find me first, and then just count, oh, 1 house down, 2 houses down. That's when I'm going to find you. Does that make sense? So this is telling someone that you are living 2 houses down from where I live. But in order for someone to actually find you, they need to know where I live first, which is where the stack pointer is pointing to. So that's why we are adding the stack pointer to the offset in order to get to the address of N. Yep.
So generally, from what I remember, normally you do return place equals 0, and then you do N equals return place plus 1.
Yeah, you can do that too.
Is there a reason why you're doing this as this code is constant?
Yeah, just being lazy.
Okay. I just
Yep. So typically you want to do something like this, because that's what exactly the stack pointer is pointing to. And then this one would be F return address 1 plus because it is one byte past that. Yep.
Okay.
So it accomplishes exactly the same thing. It's just that most of the time, you don't need a label for the return address. I mean, it's only there as a quote unquote documentation, but it really is not needed. Yep. All right, so now we have register A being N, register B being 2. And in order to do this comparison, we need to compare CMP. The question is, which way should I compare? Should I compare A comma B, or should I compare B comma A? That is the question, okay? Now, if you flip the order, it's not like, the code will not work. It's just that, you need to work around it a little bit in order to get it to work. So in this case, we want to confirm that N is less than 2, and we have a conditional branch just to do that, just to confirm that. So that makes it kind of easier. So which way do you want me to do it? Do you want to compare AB, which is slightly more natural to me, or do you want to compare BA, which requires a little bit of working around? Yes. Yep.
I was gonna say I did an AB.
Okay, it makes more sense to be AB. So we'll go ahead and do a compare AB. So I have to remind myself what I'm comparing. So I am actually performing N minus 2 right here. Okay, this is what is happening is we are performing a subtraction, but we are not storing the result of the subtraction to register A. In this case, nothing is being changed except for the flags. So after this, I know I need a J something I to a certain label, okay? So the question is, what am I supposed to jump here? There are only 5 choices altogether, okay? Because there are only 5 conditional branches. You can compare based on C, C, S, O, or L.
L.
No. No. C. Because it is an unsigned comparison. If it's an unsigned comparison, the borrow flag indicates the correct result of the comparison, whether the minuend is less than the subtrahend. When did we talk about this? Way back, yes. Yes, way back. And I did remind you guys even back then and say that this stuff is going to be useful later on, because that's what this is why we have to kind of remember that stuff, okay? Because
And we're still waiting.
you're still waiting. So if it's JCI, okay, does that mean the other ones will not work? No, it means that they won't work in all the cases. It will work sometimes, but not all the time. So JCI to some label, okay, but now I have to name the label. What does it mean when A is less than B? Well, when A is less than B, that's when we need to go to the then branch, not the else branch. So I have to name the label, correctly, so that I can say, okay, just to remind myself, this is the non-recursive case, which is the then value of the ternary expression. Which means if I do not perform the branch, this is the else expression. Okay, so I have to kind of remind myself what it means to be here, and then I have to kind of put the label over here, and this has to jump around the then. So we have to get to the end of the if or the end of the ternary expression, which I'll put here. So this way we have the overall structure of the conditional statement done. All right, so let's deal with the easy one first, because we'll deal with the then case where we just have to return N itself. Is there anything I need to do here? Okay, A should have the value of N here. Do I need to do anything? No, I'm not done already, right? Because I just chose register A to store the value of N for the comparison. So it still has the value of N right now, which means there's nothing I need to do. Okay, because register A already has the correct value when I get to line 26. If that is the case, then the only tricky part is to do it here, which means now I have to implement this mess over here. So this is where things can go a little bit confusing, because when you run this code, it is as if it is a loop. because you can see that there's a certain repetitive nature to this code. F calls F again, F calls F again, F calls F again, and so on. But from the perspective of what I'm trying to do here, which is translating the program from C code into assembly code, I don't care. I don't care if it's a recursive call or not. All I really am concerned about is, oh, looks like the last operation is an addition, because that is the sum that we are returning. But in order to perform the addition, I need to know what I'm adding, and there are two things I need to add. The first thing is the return value of f of n minus 1, and then the second value is f of n minus 2. So that means I don't have to worry about the adding part yet, right? Because I have to call f of n minus 1, then I have to call f of n minus 2. Once I have the two return values, then I can perform the add. So part of the translation process is to go over the order of what needs to happen, the sequencing of what needs to happen. And in this case, I need to first call f of n minus 1. So if you're thinking, oh no, but this means here we are somewhere in f already, and yet we're calling f, what am I supposed to do? Well, just imagine that you're calling some other subroutine, because the way we call a subroutine does not change depending on whether you're already in that function or not. So tell me again, when you're the caller, what do you need to do? When you're the caller, you're trying to call a function that has one argument and it has a return value. What do you need to do? Yes?
For your back statement.
Yep. So you need to, so I'm just going to write down what I need to do first, right? So I need to push n minus 1 on the stack first, because that's how we call a subroutine with an argument. Then we have to push the return address. Okay. And then we continue execution at the subroutine. And then we have to clean up the argument. So those are the things that the caller has to do. So now we just have to figure out, okay, fine, how do we do this? Well, the good thing is we already have n in register A at this point. So that means, oh, okay, we just have to decrement A once. So A is now n minus 1. And then what we need to do next is simply to push it on the stack. So to push something on the stack is once again a template of code. It involves decrementing D and then storing something to where D is pointing to. So decrement D, std, with whatever I want to push, which is in register A. That's going to push n minus 1 as a value on the stack. That is our argument. Next, we need to push the return address. And this is also a template of code, but you don't want to just remember this as a template of code and say, oh, okay, this is the only way that we can push a return address on the stack. Because in the final exam, I can give you alternate sequences of instructions that can accomplish exactly the same thing, but it may not be in the same order or may not be using the same instructions. You still need to understand, oh, so this is just a different way of doing exactly the same thing. Is that okay? All right. So we do a decrement D, stda, and that pushes the return address on the stack. I'm just double checking, make sure that this is all we need. Yep. Then we do a JMP I to F, which is just the continuing execution at the subroutine. The fact that F is where we are, quote unquote, where we are at, does not matter at all. Okay, so the way you call a subroutine does not matter, whether it's the subroutine that you're already in or some other subroutine. It does not make a difference. So when the subroutine returns, it's going to be returning here, because this is the place that is exactly 6 bytes away from the address of the LDI instruction on line 29. So when we get back here, I got one little thing to clean up, which is the argument n minus 1 that is sitting on the stack. And then after that, I go like, okay, we're done with the function call. The return value of f of n minus 1 is now in register A. Woohoo! We got one side of what we need in order to perform the addition. So now you go like, great, we got the left-hand side of the addition done. It's time to move on to the right-hand side. You go like, wow, that looks about the same thing. So it looks like it's about the same thing. But it's not exactly the same thing because I do not have register A containing N anymore at this point. So I just need to kind of go through the trouble to recompute it, okay? So I'm gonna do it ignoring one little point, and then we'll go back and fix that, okay? So we'll go like, okay, fine, we just need to load the value of N back into register A. So we can use, you might say, well, we can do it in a different register because we want to preserve the value of register A because it is the return value of the first call to F. Okay, so we'll say, well, maybe this will help. Okay, if I just use register B for that purpose, maybe it will save me something. I can get this done with using a different register. So LDID with F underscore N, the offset. This way we compute the address of N. And then this way we have the value of N in register B. But this time I need to pass N minus 2 to the subroutine, which means I need to decrement it twice, decrement once, decrement twice. So now register B has N minus 2 in it. So at this point, I can push it on the stack, right? So I just have to do a decrement D, STDB, that pushes N minus 2 on the stack. And then we have to push the return address on the stack. Decrement D, STDA. Oh, right, we cannot use register A. We want to avoid using register A because we are thinking at this point that that would help me save the return value of the first call or the return value of F of N minus 1. Okay, so we got the N minus 2 pushed. We got the return address pushed. So now we can go to, jump to subroutine F. When it comes back, we increment D again. Now we go like, oh, that didn't help. Because the whole time we were thinking, we want to save register A after line 35 because register A at that point, what does it contain? What is so important in register A that we want to keep it? Yes.
For the evaluation of N minus.
It has the, exactly. So register A on line 35 has the return value of F of N minus 1, which is one of the two things that I needed for the addition. Okay, so you go like, but this is not going to work because when I call F again on line 47, that invocation of F is going to clobber register A with its own return value. In other words, the way the code is set up right now, I can either have F of N minus 1 or I can have F of N minus 2. I cannot have both at the same time. So this is a dilemma, right? It's like, where do I stash the return value of F of N minus 1? You might think, but Tech, there's one more register that you haven't used. It is register C. It won't work either. Because what is the agreement between the caller and the callee? Or one of the many things that they have to agree on.
That you needed the first two registers.
Exactly. You cannot count. Yeah, go ahead.
I was gonna say that the return is always in register A, and another two is taking whatever.
Yep, exactly. The callee or the function that is being called can change any one of the registers. Register A being the only one that can hold a return value, but otherwise, register B or C, the callee, the function being called, can cooperate anyway it wants to. Okay, so that means we now have a little bit of an issue because putting that register A in register C is not going to help. So I'm just going to put in the wrong code here to show you what is not going to work. This is not going to work. I cannot count on register C still containing the return value of F of N minus 1 by the time I get all the way down to here. But this is not the first time we encountered this problem. The first time we encountered this problem was when I talked about the sample program that has Johnny 5 and Brian, which is 7 of 9, in order to compute 12. How many people remember that particular program? Okay, so I basically leave behind Easter eggs, when I talk about sample programs. That is the trick that you need, because you basically have to say, oh, so that means I have to push f of n minus 1 on the stack. And then later on, we pop it in order to use it for the addition. Okay, so now we go like, okay, well, easy peasy, we'll fix that. So we go back to the return point of the first call, which will give us f of n minus 1. And we just go like, okay, fine, we'll just decrement d, and then we store stda. And this is basically pushing f of n minus 1 on the stack. Cool. So now the code should work. They go like, no, but there's one little problem, because now the stack is no longer in the same state as it was at the beginning or the entry point of the subroutine. We have one more byte sitting on the stack now. So what the stack looks like is it is now directly, the stack pointer is directly pointing to the value of f of n minus 1. And then on top of that is the return address. And then on top of that is n. So n is no longer just 1 byte away from where the stack pointer points to. It is now 2 bytes away from where the stack pointer points to. Every single label, all the offsets to everything that is on the stack, local variables and parameters, are now 1 off. Which means when I look at the offset, I have to now remember, we have to remember to add 1 to it because of this additional push. Are we still doing okay so far with this? So this is a combination of a few things that we have talked about in several sample programs. But each one of those sample programs illustrates one important point that is consistent with the caller-callee agreement, which is basically the centerpiece of everything that we have talked about since we talked about calling and returning. Are we doing okay so far at this point? Are there any questions about the program that we have at this point? Okay, yep, go ahead.
What module can we find out reminder where LDI b comma dot 6 plus exact?
I think we talked about this 3 times already. Of course, I cannot remember exactly what dates, because that is not my job to remember. The dot is the address of the LDI instruction. The 6 plus is the postfix notation of saying +6. So it is really important to keep track of what I have talked about in each class and put it in your own notes so that you don't forget. Yes, I really hate to have to nag, because I can see some people here are kind of not liking me nagging either. But since the question was asked, I have no choice but to nag. All right, so now what do we do? What do we have at this point? What is register A on line 53? By the time we get to line 53, what is in register A? We just, yep.
Well, we just pushed it on the stack area, changed it.
Not yet. We haven't really done anything with what we pushed on the stack yet. This is after we return, right? So after we call f the second time with f of n minus 2, it got back to this point. We clean up the stack. That's how we get to line 53. So at this point, what is in register A? Register A has the no -2, because this is the second call. Nope, it's in register A, because according to the caller-callee agreement, the return value is always in register A. Register B doesn't do a single thing. Okay, all we did is to use register B to put what we need to push on the stack. But other than that, register B has no particular value. The return value is always in register A. So on line 53, register A has the return value of the locked call to F, which is the result of F of n minus 2. Is that okay? Yep.
So what you're saying is it hasn't been written yet? Has it not been written yet since we,
It's not in written.
or, because the last time we touched A, we pushed function n minus one, and I think that's where our confusion is.
That was before, right? So on line, after line 35, register A had F of n minus 1. And that's what we push on the stack.
Right.
But once we push it on the stack, we didn't do anything with it. It's still on the stack right now. So from line 40 all the way to line 51 is the second call to F with the argument of n minus 2. So by the time we get to line 53, register A has the return value of the second call, which is F of n minus 2. You had something to, you were trying to say something earlier. Go ahead.
Or yeah, I think, well, it's okay. It seems like the last time we pushed A, I think what we were thinking is that between lines 40 and 51, if we had replaced B with A, we would probably normally do it.
Yes.
Is that what you're assuming that we're doing here?
But it doesn't matter which register you use for, so if you replace the use of register B with register A or register C between line 40 to line 51, it would not have made any difference. So that means, all of these register Bs, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you change all of these to register A, it wouldn't have changed anything. If you change all of them to C, it wouldn't change anything from the perspective of the correctness of the target. Because until you get to the return point of a subroutine, register A is not special at all. It is only when you return a value to the caller, then register A is special, because that is the agreement between the caller and the callee that we would use register A to store the return value.
Would it be like illegal to expect that, like, if you put something in register B and register A while you're in a function, would it be like not allowed to expect that register B will still contain that value when we get back to function?
Nope, that is not the agreement. The agreement says, the called subroutine is free to clobber any register. That is the agreement. So that means, the real important part here is to understand what is the agreement between the caller and the callee. And that is, so I'm trying to point out, all the important stuff that you probably want to either revisit or kind of put it into your own words when you take the final exam. Hopefully you will understand the concept before you take the final exam, because just having the notes with you in the final exam is not going to help. So we have caller-callee agreement, and then we have the caller-callee agreement / contract. They are basically the same thing. They talk about exactly the same thing. If I click on it, we basically say, okay, let's see, right here, the values of register A, B, and C are not assumed preserved. That's part of the agreement. Is that okay? So this document is really important because everything that we do is based on the contract. This is the contract between the caller and the callee. We can do anything as long as it is still compliant to this contract. Is that okay? I mean, are we understanding, where to find the agreement and how to read and understand the agreement? Because all of the things that we have talked about are basically just results of this agreement. Yes.
This is the memory of registers A, B, and C. When you assume they're no longer preserved, is that based on frame or just
Based on what?
how long can a value be held in register before you assume it's not valid anymore?
The moment you do this, all bets are off. Yeah, the moment you transfer, the moment you continue execution at the entry point of the called subroutine, all bets are off. Register B remains as a stack pointer. That's the only thing that prevails between the caller and the callee. But the values of the registers, the callee cannot expect anything in any specific register, but the caller cannot expect the registers to be preserved either. Yes.
To kind of, excuse me, to kind of understand a little bit about what's going on with register A. Not that it's like the correct footprint of things, but could you, for the sake of visualizing it, basically take F, the code up to this point, and basically replace that JMPI F with the code of F, so that you can kind of read through and go like, okay, so each line is doing this, doing this, doing this, and then you can see by the time you get back to A and then D, that register A now has this new value, like you can see what's going on.
Yes.
It's kind of like that debug tool, not debugging. But
Right. But we already have a tool that can help to visualize. The trace analyzer actually gets the same thing done. Because with a trace analyzer, we can actually see what happens after line 50. You can see, that code before we get back to this point, it's going to clobber, the registers. Whatever registers we use here, they're all going to be clobbered. How do we know? Because it's a recursive call. So whatever register we are using here, it will be the same registers that will be used in the recursive call. Does that make sense? Okay. All right. So this is one thing we know. Register A has the return value of f of n minus 2. So what does the stack look like at this point? So we want to look at the stack. So the stack, or a part of the stack, is going to look like this. We have n, we have the return address, we have the saved value of f of n minus 1, and that is what the stack point is pointing to right now. Okay. So what do? We got the two pieces of information that I need. I have f of n minus 1. Take that back. That is actually correct. Okay, never mind. I got everything correct. So we have f of n minus 2 in register A. We have f of n minus 1 being pointed to by the stack pointer right now. So what do I need to do in order to return the sum of f of n minus 1 and f of n minus 2? We got all of those. We got everything computed. It's just a matter of getting to those values in order to perform an act.
Yeah.
So we do a pop, which means we have to load first. Yep, that. And then don't forget the increment D, because the increment D is necessary, because otherwise the stack pointer will still be pointing to this thing, which is no longer. Exactly, then we'll end up using it as a return point, as a return address, which will just land you on La land. So your program will look like it's a loop because it's going to land on a really low location, and it will just repeat that code over and over again. And that would make it look pretty confusing. All right, so now we have register B containing f of n minus 1, register A containing f of n minus 2. So I think an add AB will do what we need, and then we can just go around the then branch and exit and return to the caller. Is that okay? Are we ready to go? Okay, so we can test this code. Okay, I can give you guys a little bit of time to take notes, particularly not so much to copy the program itself, but to capture your understanding of all the little things that we have to do in this case, like why do we need that extra 1+, okay, in the offset, and why do we need to push the return address on the stack? Those are the important things that you need to understand and put it in your notes. The program itself, I can just send you the code. I mean, that's not something that you have to kind of spend time to write on your own notes. Yep.
So for 59, you're loading the buckets of D into B.
Yes.
Where the buckets of D is still the
We are putting the results of f of n minus 1 in the register B.
then you're getting rid of D entirely.
I'm not getting rid of D. I am moving the stack pointer.
Yeah.
So it's no longer pointing to something I do not need anymore.
You deallocate it.
Yes,
Mistakenly within B.
yes. So,
Next,
yeah, go ahead.
next you're taking that value and you're adding it to A, which is F n minus
F of n minus 2, that is correct. And I accomplished adding f of n minus 1 and f of n minus 2 as a result. Any other questions about this code? So this is why this code is a little bit tricky, even though it is shorter than the verbose version of T factorial, because the verbose version of factorial has a formal local variable acting as, oh, this is the extra thing on the stack that will help store one of the return values. So that's why that code is easier to understand, because you don't have to apply all the tricks that I have to apply here. All right, so do we want to give this a try, make sure that this works? Okay, so we'll go ahead and set up a test case in main. It's using 3, I'm gonna bump it up to 8. I think that's supposed to be what, 21? Okay, and it's gonna take a little bit of time to do too. So we'll go ahead and give it some time. Okay, so documents, CISP310, with a spider. And this is flip.ttpasm. And I can switch to the browser and go back to the assembler, go to the analysis tab. And this is going to be a long trace too, because the amount of time or the amount of the length of the trace is proportional to 2 to the power of n. So 2 to f of n, f of 8 is going to take a long time to compute. All right, so I'm going to go to the summary here to note, oh, okay, it did not take too long. It's only 52 rows to get it done. I don't think so. It is 52. All right, so the question is, did I get the computation done correctly? It is storing a 1a into fe, which I believe is variable x in main. 1a is 10 plus 16, which is, that doesn't sound right. 10 plus 16 is 26. And f of 8 is not 26, I don't think it is.
For 7?
Hmm?
For 7 should be 13.
Hmm?
For 7 it should be.
This is f of 8.
Oh, 8.
Yeah, f of 8 is supposed to be 21. Yep.
Yeah, that should be 15. That's
15 in hexadecimal. Okay, so I think I got it wrong, but I could be wrong here too. So let me check main and see what it does. If it is wrong, I'm actually kind of happy, because now I can show you how to debug the program. I have not been able to show you how to debug a program because I have not made a mistake in all these programs that I write in class. All right, so this is main, and in main okay, I haven't changed the test value. I'm still using 3 as the test value. Okay, and then we call f, we come back, and then we store the return value into whatever b points to, which is the local variable x of main, and it returns a 0. And in main, we allocate LVS, and that would be 1 byte on the stack. And that would be location FE. So that is correct. So we are still using the test case of 3, and I can tell that we are using the test case of 3 because that is the argument that we are using. So if this is the argument that we're using, f of 3 is 2, if I remember correctly. So that means FE, location FE, should be updated with 2 and not 1A. All right, so I can officially now tell you that the program is not working. And let me just look up the last time register A gets updated. Or am I looking at the wrong part? Yep, I'm definitely not, the program is definitely not working. Oh, okay, so this is interesting. This is the exit code. And we are storing A to B, register A has 1A in it. So I'm basically running the program backwards and say, okay, how does register A get a value of 1A? 1A seems to be the return address, and somehow I'm using that to return. All right, so this is good because officially I can now say that the program is not working. So now how do we hunt the bug down? What do you think? Just a general approach. If your program doesn't work, how do you get to the bug? Yep.
That's under CISP. Yeah.
As abundant as you can possibly get. Every single instruction has its own cout right here, right? Okay, so now what we need to do is to follow the execution of the code and see when it is deviating from what we expect it to do, okay? Which also means you need to know what you are expecting the program to do first, because it's just a flaw, it's just a minor mistake that I have made. All right, so we'll do it line by line, okay? So you might want to mark this time too, because this is actually important when you are debugging a program. So this is a general debugging technique, at least in this class. Okay, nothing to speak of here. Initializing the stack pointer. This is the return address to the entry code that has no name. And then we push it on the stack, and then we continue execution at main. So we are basically calling main. And now we are reserving 1 byte on the stack. So the stack pointer is decremented by 1. So everything is still good. We load the 3 into register A, and then we push it on the stack because this is our argument to call F from main. And then we push the return address on the stack. So 1A is significant because it is the return address. So somehow I'm using the return address as a return value. So I have a very strong suspicion of what is wrong with it, but we'll go ahead and see if that really is the case. Because if I use, when I return, if I use register A for the LD, AD, that would account for this, but I'm pretty sure that's not what it did, but we'll find out exactly what's happening here. So JMPF, and then we end up on at the first instruction of function F. So the first thing it does is LDBD, increment D, and it returns. So this doesn't sound right to me, because this is going to the entry point of F. At the entry point of F, I'm also basically just doing a return code right away. So that is wrong to me. So now we kind of have found the problem. So the problem is on line 11. Line 29 somehow landed on line 11, and line 11 is basically just the return code. So something very, very wrong has happened. So we go back to line 11 here, and here we go. So what just happened here? Did I use the wrong program? This is not the program that I wrote. This is like before, this is the template before I actually wrote the code. So the problem is, where did I write that code? we have a bigger problem now. I think it's FIB3. There we go. Okay. We were running the wrong program. Yes, this is extremely embarrassing because this happens in real life as well. Sometimes I will run a program and go like, it's not doing what I think it should be doing, not even close to what it's supposed to be doing. That is the wrong file. All right, so it was the wrong file, but you can see how I track it down. It's like, wait, it gets to the entry point of the subroutine and it returns right away. I'm pretty sure that's not what I wanted to do. Yep. Yeah. All right, so we're gonna test it again, but this time with the program that I just wrote, okay? which is fib-3, not just fib. All right, so this time it took a little longer, and I hope it didn't time out because the script actually has a timeout feature, which means, if it took too long to run, it would actually terminate Logisim before it's all done. So now we will take a look. So if I just look at summary, it is a lot more reasonable. This time we have 2,736 lines long in the analysis. So we'll just kind of get to the end and see if that's the correct end outcome. Yeah, I know I can just kind of do this, right? Here. 2,700 something. There we go. All right. All right, so this is good. Okay, this shows us that we did end up with a halt instruction. Excellent. The stack pointer is back to 0, 0. So that means the stack is balanced, which is also a very good sign. What I really want to know is what is in location FE. It is 1, 5, so I got it. So now I'm disappointed because at first I thought, oh, great, I made a bug. Yeah, I made a mistake in the program. I can show you guys how to debug a program. No, I did not. I'm sorry. Just change the file name to fib-3. Did you guys realize what I made, or what the mistake that I made earlier? Why the first time I ran, it didn't happen the way that I thought it would? I was using the wrong code. Yep. All righty. So do we have any other questions about this program before I move on to the kind of like a quick introduction to the program that you need to write to turn in next Thursday? Yes.
I just want to make a comment. If
Yeah.
you did any 13, it would, for my project specifically, it took to line 44,000. And surprisingly, the script didn't time out.
You did not? Okay. I might have taken out the timeout or specify a long time to timeout. Which number did you use to test the program?
It was 13.
13? Apple 13?
233 or something.
Yeah. Cannot remember who got the hand first. How about you personally? Yeah.
You said that it's something to do on Thursday, but it says it's due on Saturday.
Oh, okay. I will need to change that. It will be next Thursday. Sunday?
Yeah, the Sunday after the Texas.
Oh, okay. It'll be next Thursday. Go ahead.
So just kind of a quick question about when we put the return address.
Yeah.
Specifically, you had 6 to the value. How did you determine that it's 6 and not some other number?
Oh, okay. You mean the .6 class?
Yeah.
All right, so that really is something that we have talked about several times. So the way we do the counting is we wanted to jump back to this location here. So the way we count is LDI takes 2 bytes, decrement D takes 1 byte, STDA takes 1 byte, JMPI main takes 2 bytes. So you have 2 plus 1 plus 1 plus 2, so that's a 6. Yep.
So it jumps, it returns between 6 and 7 or on 6 or between 7?
It returns to the address corresponding to the halt instruction.
So it returns on 7, then does 7?
Yeah. It continues execution on line 7 with the halt instruction.
And we will, if we want to use this in our own code, we would have to memorize the number of bytes we want to offset.
Well, I mean, all the something I instruction, they all take 2 bytes, and then everything else only take 1 byte. Yeah. Because the immediate operand takes the extra byte in addition to the opcode. So if you do not have a something I instruction, the I stands for immediate, then it's only going to take 1 byte. Righty. Any other questions about the Fibonacci program? Now I can talk about the verbose version of this program, or we can talk about the program that's due next Thursday. Yep.
So I was curious how you about it. I know you just said the 6 plus. Can you walk us through your process and how you like, this is 2 plus 1, like, where did you?
Okay. So the best way to understand that part is to look at the assemble tab. So when you look at the assemble tab, you can actually see it because you can see on row 3 here, you can see it, the address is 03 and it takes up 2 bytes. And then on row 4, it takes up 1 byte. On row 5, it takes up 1 byte. And then on row 6, it took up 2 bytes. So you're basically adding 1, 2, 3, 4, 5, 6. So that's why the location you want the function to return to is 6 bytes away from the 6C. And that's what the dot is referring to. Yep.
Another thing that you could do is you could look at the opcode table and when you're looking at this, there's a lot of them have a description that whatever even using follow that like but I was going to ask, so if you have a large enough number within like your n value, you would wind up erasing out a portion of your main code, right?
Yes.
Okay.
Because your code grows from low address to high address.
Yeah.
And then your stack starts with the very highest address and grows down. So when your recursion takes more stack space than you have, then it will clobber your actual code. And bad things will happen.
Okay.
Very bad things will happen.
I thought so. I just
It's basically, it's not a stack overflow in the sense of, what we normally associate with stack overflow. In this case, you're running out of stack space. So you're not using a stack overflow in order to hack a program. You're basically just clobbering the original program.
How much would it take for like a regular processor nowadays?
You want to know? You can see Taxia reactions like, you want to know? Let's find out. Yep. Okay, so we just have to write a program like this, okay? Oh, actually, I can do better. This is redundant. I don't need that. Because I can do this. All right, so this is where the debugger comes in handy. Okay, so I'm going to show you guys why the debugger is really handy if you want to do something like this. Okay, we compile the program. If you just run the program itself, it will just give you segmentation fault. Segmentation fault is only telling you one thing. You're accessing a memory location that you're not supposed to. Is it in code space? Is it in stack space? Is it in heap? It doesn't tell you whatsoever, right? So that's why the debugger is going to be helpful, because the debugger will tell you where in your program is triggering this particular segmentation fault. So now you say GDB, same program stack, and then you just run the program. And it's telling you that the code is in main 3. So it is still not telling you the stack space, like how big the stack is. So let's go ahead and redo this so that we can actually understand how big of a stack we have. So we put a breakpoint on line 3, and then we start running the program from the beginning. So now you have to do an IR here, which looks at all these registers, actual registers. So RSP is your actual stack pointer. So where's RSP? It's right here. So this is your stack pointer. You can also just say print, I think RSP, and that will give you the same value. Okay. So now you run the program. You continue the program, and you want to delete the breakpoint, delete the first breakpoint, because otherwise it will keep stopping every single time. So you delete the breakpoint, you continue until it stops. And then what you do now is you ask it to print the stack pointer again, and you can basically ask it to subtract this from the original one. And what is it's $1? Okay, there we go. So that is the number of bytes on the stack that is allocated to your program. I mean, there are some extra stuff that has taken space already, but that gives you an order of magnitude of how large the stack is. So how big is it? So it's about 8 megabytes. It's not a whole lot. Because normal programs should not need a lot of stack space. And this is also why recursive algorithms are frowned upon. Because you cannot predict easily how much stack space is going to be used. Because it all depends on how big is your N. Is that, yep.
Does this vary between processors? So if I test on my computer,
So if you have a Mac, especially the one using an M2 processor, then the name of the register would not be RSP. So you have to look up the name of the stack pointer using with your particular processor or architecture. But GDB is universal in the use of the $ and then the name of the register. So the approach would still work. You just have to find out what is the name of the register, stack pointer register for your architecture. All right. Yep.
I think what Jared was kind of trying to ask was, if you were to buy like the top of the line CPU and mid grade CPU, would those both have the same number of bytes, give or take a little bit?
It is determined by the operating system.
Okay.
So depending on the operating system, when it creates a process, it will give you a maximum number of bytes on the stack. It doesn't really allocate any of the pages because of virtual memory. So if your program only takes 8 kilobytes to run on the stack, it's not going to take up any more than just 8 kilobytes. It will allocate as it goes, but it has a maximum of how much it is willing to allocate, and that part is OS or operating system dependent. There may be some parameters you can pass to the operating system and say, I need more, or I want to be less, and so on and so forth. But normally there's a default value based on the operating system that you're using.
Okay.
All right. So let me take a look at the time. It's only 36. We still got plenty of time. So we are going to take a look at the beginning code of the program that's due next Thursday. So let me go to announcements again, because I think I sent that code to you as an announcement as well. It's pre-zip updated. There we go. This is the latest one. Okay. And I should not need to download it because it should still be on my computer, but let's download it anyway. Oh, I guess it's not, because mine is called tree and not 3-1. All right, so we get here, make it dirt 3. Oh, it's already there. Minus. If anyone is attempting to ask tech, have you ever heard of the term of a GUI? Yes, I have heard of that term. All right, so let's take a look at just the tree.ttp ASM, because this is the entry code. This is the template code that I'm supplying already. It has the static local variables. There's a subroutine here. And the first thing I'm going to do is simply to put a halt here. Okay, so if I put a halt here, that means the subroutine is not done, but you can actually see what is happening at the entry point of the entire subroutine. And that will give you some idea of how things are arranged, and hopefully that will be helpful already as you move on to continue to write your program. So that's what we'll do. And there are several ways to do this. I can do it in the GUI mode, and you can just examine the RAM location, or we can go into the trace analyzer so you can actually see how things are being done. So I think that's a better way to look into the trace analyzer. So we are going to go back to use River Spider. So we'll submit tree.ttp ASM. Now, all of the things that the River Spider can do can also be done manually. So it's a little bit more time consuming, but it's not impossible. I've done it for years before I wrote this script to kind of make it easier on myself. All right, so we'll go all the way back to just the first row here. All right, so we'll just go ahead and explain what each line is doing. So no op doesn't need to explain. I don't have to explain it. Initializing the stack pointer to 0. Okay, this we just want to make sure that we start at the location past the end of RAM. This is pushing the return address on the stack, and then we continue execution at the main as just a subroutine. This one is allocating 6 bytes on the stack. So why are we allocating 6 bytes on the stack? What are those 6 bytes? So we have to go back to the source code to find out what those 6 bytes are. So we have to go to look at 3.ttp ASM and then look at the entry code of main. All right, so that all has to do with, they all have to do with line 35 to line 37. What are those lines doing? What are they defining? What are those labels? They are offsets from where the stack pointer points to the various items on the stack. So we are basically saying after allocation, after we allocate for the local variable space, the stack pointer should end up pointing right at R, which is the array of 5 characters. Is that okay? And then after that, we have APTR, which is at location 5, counting from where the stack pointer is. So now the question is, okay, so can we talk about these things as concrete locations in RAM and not just, oh, this is so many bytes away from the stack pointer? The answer is yes, we can, because we can now switch back to here, because these two instructions combined is allocating for the local variable space, which means after this instruction here, F9 is where the stack pointer is pointing to. So that means F9, F8, FB, FC goes and FD, okay? From F9 to FD, those 5 locations are corresponding to R, which is the array of 5 unsigned 8-bit integers. The next location, okay, 9, A, B, C, D, E. So location FE corresponds to APTR, which is the pointer that you allocate in main itself. Is that okay? Yeah, so let me see if I can kind of use a picture to represent it. So location FF is the return address back to the caller of main. Location FE is APTR of main, and then FD, F9 to FD would correspond to R, which is a 5-byte array. Is that okay? But that's not when the program stops, okay? The program did a little bit more than that before it stops. So we allocate for the local variables, and for the last time, LVS stands for local variable size, because I got that question quite a few times. All right, so now we do the initialization. So the initialization is to put the address of the array R into the local variable APTR, which means if you look at the way we put it here, so that means F9, which is the address of the entire array R, should be stored in location FE. That's what we should be seeing in the trace, and that's exactly what it has done. So this line is corresponding to APTR equals to R in main. Are we doing okay so far? Because knowing what local variable of main is where is going to help you debug your program, because array of traverse is the address of APTR all the time. And what is the address of APTR? It is FE. So you should be pushing FE as array when you're doing the recursive call. If you're not seeing that, that means something is not going right. All right, so after that, okay, let me see what is going on here. So after that, we call the traverse the first time. So when we call traverse, we have to push the arguments backwards, which means the last argument is pushed first. So what are we pushing first? We're pushing whatever is in register B first, because we are pushing the address of APTR first. let me show you the C code because the C code, okay, vertical split. And then look at the C code on this side. Okay, on line 34, do you see how we are trying to push the address of APTR? That's why we push the FE on the stack the first time in the trace. So this is the push of the address of APTR. And then this one here is the push of, in this case, the address of N1. The address of N1 is 0A. We can confirm that by looking at the assemble view, because in the assemble view, if you just kind of scroll around a little bit, you can see main underscore N1 is starting at location 0A. So that's what the 0A is. It is the address of N1 as a node. So that means by the time we get to traverse, what we can expect on the stack, as far as traverse is concerned, we can expect the address of APTR, which is just known as array, as the second parameter. And then we have PTR as the first parameter. And then we have the return address. Those are the three items on the stack at the entry point of traverse. So this is important because when you're debugging a program, I would suggest that you use the trace analyzer. As much of a pain as it is to use it, it also gives you a lot of information about what happens when you run the program, which is very, very valuable because if you run the program in GUI mode, and the memory locations are getting clobbered over and over again, you cannot see the clobbering because you can only see the result of all the clobbering, but you cannot see the sequence of what is clobbering which location with value. Using the trace analyzer, you're basically looking at the entire execution of the program. Every single overwrite of every single location you ran is documented. So that's why it is really helpful to use the trace analyzer. So we still do okay so far with this code here, because what we have here on the stack, okay, I'm just going to finish this lecture with this, is at location FF, we have the return address, so the main can return to its own caller. We have location FE being APTR of main, and then we have location F9 to location FD being the array R, and then we have location F8 being the parameter of array, which is being passed to traverse. And then we have location F7, being PTR, which is the first parameter of traverse. And then we have location F6 being the return address of traverse. That is what is on the stack at the halt instruction. Is that okay so far? Knowing how to dissect, what the stack looks like and what each location is corresponding to is going to be helpful. Because if you see a value and you think I should be seeing this value over there, but that's not what you're seeing, that means something has gone wrong already. Then you have to go to an earlier point, okay? Keep looking backwards. You don't have to run the program again. All you have to do is to scroll up in the spreadsheet, and then you ask, does that make sense? Does that make sense? So you have to go all the way back to a place where things are still making sense, and then go forward again until it does not make sense. That's where the problem is. All right. So I'm going to stop the lecture now. We are going to transition to the lab. I will be at the lab. So if you want to write your code and want to know how to run the trace analyzer and stuff like that, I can be there to help you. You'll kind of take a look at how you do it. Or if you run into some problem, like your program is chewing up stack space until it runs into the program space and the whole thing just kind of died a horrible death, I can look into that too. I can try to kind of help you understand what is going on with your program. So that's what we're going to do in the lab today. So that means, if you think I can just go home and do this program myself, hey, that's fine too, not a problem. But I'm just telling you that I can be a resource if you want to look into what is happening in your program. There are no actual lab. We're just going to continue to write this program. until next Thursday. So there are no additional new labs after this point. All right, so I'm gonna fix the due date of the lab first, I mean the assignment, and then I will head over to the lab.
I'm not gonna score or.
Okay, hold on a second, let me end the